Speak about graph-based binary analysis. First off, I'll give you a short overview of what the talk will consist about, or consist of, and what it'll be about. First off, I'll give a short introduction in terms of what are graphs and what kind of graphs I'm talking about, and why I'm talking about these graphs and why I think they're particularly useful. The second part will discuss simple flow graphing, which is pretty much just taking a sequential bit of code and creating a graph which clarifies the interdependencies and the code flow. I specifically address some problems you'll encounter when dealing with Microsoft's optimization or ways of optimizing code these days. Secondly, I'll talk about reducing flow graphs step by step or gradually to allow you for manual decompilation. Basically, graphs can be very useful if you have to create C code from assembly. And I'll finally talk a little bit about using these flow graphs to improve fuzz testing, stress testing tools, and to get a better idea of how much code you're covering and so on. Afterwards, I'll speak about structure and object reconstruction. Usually, or specifically, these things, structure and object reconstruction, can be achieved by creating certain graphs which track the control. Well, they're basically forwards data flow graphs. They track which bit of code in the program has control of a certain pointer at a certain point in time. I'll then speak a little bit about vtable parsing to improve object reconstruction. And finally, I'll speak about variable control graphing. Basically, that would be inverse data flow. Well, if you find a pointer somewhere in a program and you want to find out where this pointer came from, that would be a buffer definition graph or inverse data flow or whatever you want to call it. Now, there might be the question what this has to do with security. I've gotten this question before, so I'll try to explain why I think these things are interesting. First off, the second part about decompilation and manual audits. Code graphs, like simple flow graphs, help massively in decompiling stuff and help massively in understanding code better. So this improves the efficiency when you have to do stuff like manually finding bugs in software, or alternatively, if you ever have to decompile stuff for somebody, like, I don't know, there's people who can't read assembly language, then you have to give them C code or whatever. It'll massively increase your efficiency and make you less error prone in your work. The third part about object and structure reconstruction, pretty much, well, the slide says it speeds up manual binary audits, but to be honest, it just makes them feasible at first, because reconstructing structures and objects manually will take forever and a day. So before you ever get to finding bugs, you would be reconstructing structures and objects for weeks and months. Secondly, the pointer control flow graphing can be used for massively more sophisticated automated analysis at some point in time. I don't think I'll speak too much about the more sophisticated things you could do with these graphs. That might be something I'll be covering next year or at DEF CON this year. I don't know, we'll see. And finally, the inverse variable tracking is relatively useful if you have to manually audit code and you want to do buffer size arithmetics. For example, you have this string copy call and you want to find out what size all buffers which go into this call are. For example, is the target buffer larger than the source buffer for every possible combination of calls or every possible code path? You want inverse variable tracking because the string copy will probably take a char pointer which has been passed by a target by a calling function, and that has gotten 3 char pointers by its calling functions and so on. So in the end, you got 20 or 15 different char pointers going in there, and you want to estimate the buffer sizes of every single one of them. Okay, so what is a graph? The graphs I'm speaking about are just simple flow graphs. They consist of nodes of sequential code and then links between these nodes. Why should one use graphs? Well, first off, graphs make code understanding a lot easier. Well, computer code, while being sequential in memory, is not really sequential in execution. I mean, we have large blocks which are being skipped and so on. So it doesn't really make sense for a human being who tries to understand the inner working of the code to read it in a sequential manner. You want to know the interdependencies, you want to know which parts are being skipped if a certain part is executed, and so on. So graphs make code understanding a lot easier. Human beings are not particularly suited for reading large amounts of sequential code, but we're very, very visually oriented. So everybody loves flowcharts because they make things a lot more visual, a lot more easier understandable. Complex issues can be clarified quite a bit by graphs. If you've ever had to deal with multiple nested loops in the disassembly, it is quite annoying. You'll see that later on with the decompilation, that using graphs and reducing them slowly will give you quite of an advantage. Well, furthermore, graphs, directed graphs, are the only valid abstraction for single-threaded computer code. Now, having a valid abstraction for something is relatively valuable because you can start doing more sophisticated analysis on it. Which means, without the abstraction, you can't really do stuff like automatically find bugs. An abstraction is the first step to more research. And graphs specifically have been studied quite a bit, so you got a whole library full of relatively well-designed or well-thought-out algorithms which you can use on paths, on graphs. For example, exhaustive path search to see whether there's a path between two nodes, and so on and so on. Well, last but not least, graphs are really easy to generate, and well, there's lots of tools which display graphs. Therefore, you don't need to write too much software on your own. Now we'll get to simple flow graphs. As I explained before, they're pretty much just taking a sequential function and splitting it up into its control blocks and then drawing arrows between those. They simplify code understanding, they clarify code interdependence, and what I find them particularly useful for is the gradual manual decompilation. I frequently have to give people who are not capable of reading the functions themselves decompiled code. And decompilation is, well, when you do it manually, a freaking nightmare. And when you do it automatically, it's probably even more of a nightmare. So, well, we'll play a bit with these first. IDE 4.17 and higher include a built-in flow graphing plugin, which is on the F12 key. Unfortunately, it does have, well, a few disadvantages. First off, the output, like the graphs that they generate, are being exported into a file. So it's not like you can write a plugin which directly gets the data structure from IDE and works with the graph. Secondly, the file is temporary and hard to find, so they're not really very friendly in telling you where the file is at. There's more problems with IDE's built-in flow graphing engine, specifically when it comes to Microsoft's code. But luckily for us, building a function flow graph is really easy. You pretty much start at the beginning of a function, you trace the code downwards, and whenever you encounter a local branch, like a jump, a conditional jump, or an instruction which is target of a jump, you split the graph, which means you have a sequential bit of code, you parse it down, you encounter a graph, so now there's two ways you could follow. So now you follow both two ways recursively, and you just go on, and you just continue until you find a node which does not have any further downlinks. You might have to handle switch cases, well, separately, because switch cases kind of divert from this normal scheme. You could normally make the assumption about computer code that there's always, like, every node in the graph only has two downward arrows, because it's only branch taken or branch not taken. But in the case of switch statements, you have basically an index into a jump table. So all of a sudden you have a node which can have an arbitrary number of further downlinks. Oh well, we all know these graphs more or less. IDE's built-in flow graph looks something like this, which is a bit nicer to read. And I've built my own graphing engine, which has a few advantages, amongst other syntax highlighting, which pretty much does the same thing. So function flow graphs are relatively simple things. Now, Microsoft has come up with a relatively original way of optimizing the binaries. Recently, GCC has started to do similar things. I'll explain that in a minute. Basically, the idea is that starting from the Pentium 3, it becomes relatively important that, the Pentium 3 itself would cage memory with instructions. So it became important that you have as much memory as you actually execute as possible in one spot, which means you do not want the usual way a function looks like anymore. I'll explain this. You have the beginning of the function, then it jumps over some kind of code into the regular code of itself, and finally returns. And in between, like intermingled with the code that almost always gets executed, you have error handling routines. If something goes wrong, do this. So you got pieces of code that hardly ever get executed, and which are in the same place or which are in the sequential block of the function. So what Microsoft does is they start generating graphs and set breakpoints on every graph node, and then they start collecting profiling information, which means they'll see what the usual way the code will go is. And if you have, in 1,000 executions, execute the regular code instead of the error handler, they decide that you don't need the error handler at this location. So they cut it out of the function. Now this is the length of the function before their optimization. They cut it out of the function and move it to a different page. So the less trodden path, the path that is usually not taken, is moved somewhere completely else, and the function itself has shrunk. So we got simple, pages in memory which only contain code which usually gets executed, which improves the paging performance of the operating system because you don't have to, page in and out quite as much, and improves caching in a big way. Recently, GCC has started to do similar things where they start merging blocks of functions. Basically, what the compiler does is they analyze all the functions that they're generating while compiling. And functions, all functions have a standard epilogue usually. So if there's two functions which at a certain point in their graph are identical, usually at the very end, they will merge the code blocks so that multiple functions have the same bit of code they execute at the end, which looks relatively funny. The problem with these kinds of optimization is they will totally screw up IDA. IDA, in its internal engine, makes the assumption that functions are sequential bits of code, or sequential pieces of code. And that is so deeply into the IDA, inside the IDA kernel, that Ilfak is really dreading to change this and really does not want to do it. And therefore, in these fragmented functions, you get neither stack variable tracking, you get, can't even graph them in the first place with IDA. So there's massive, massive problems. And it doesn't seem like Ilfak makes it much of a priority right now. I'll demonstrate the problems we have with graphing functions. Here we have the RTL free heap function in XP, and it is fragmented. As you see down there, you have multiple, the normal function flow graph would have a, would look like this more or less. We'd have one point of entry, then it would branch out into many, many complex bits of code, and then slowly converge against the return instruction. So what we see here is we have the usually trodden path of code here, and all other paths of code have been moved elsewhere. You have a jump somewhere in the binary, and the grapher really can't deal with this and IDA can't either. So this is massively annoying when you have to decompile, like, for example, a heap implementation, which is something that is relatively useful for exploitation or finding bugs or similar things. So my graphing engine does deal with this, and by just not making the assumption that a function is sequential, wait a second. I get a nice and complete flow graph of the entire function, which is a bit nicer and, massively more useful. Okay. So I spoke before about the fact that simple flow graphs are useful for manual decompilation. Manual decompilation is really, really, really tedious. It takes forever. It'll burn you out easily. And the problem is that you need to have a very good understanding of the structure of the function which you're decompiling. So frequently when you do the sequential decompilation stuff in sequential code, you make this assumption like, oh, I'll look at that branch later. And then you go downwards, and this branch would have changed the entire structure of the function. You have to rewrite the decompilation, and it all gets messy and messed up, and you have, well, no clue what's going on anymore. Secondly, it's really hard to track progress with decompilation if you do it sequentially, because you start reading the code, the function seems huge to you, and until you're done, you have no clue how far you've progressed so far. So this really smashes your motivation in terms of, Jesus Christ, I've spent 2 days on this and haven't gotten anywhere. Well, in fact, you've covered like 90% of the code, but you don't know it yet because you haven't reached the end. Furthermore, I'm in the situation that I have probably a total of about 12 to 13 weeks a year which I can devote to computers, which means in the meantime I'm constantly doing something else, which means every time I start something, I'll be interrupted and then I'll have to get back to this later, like a week later or 2 weeks later. So if you're decompiling something, you're really screwed because you start reading this huge function, then you have to stop, and 2 weeks later, oh, did I look at this branch already? Have I covered this? Shit. And sorry, it's like I've lost so much work for stopping for a few days and then having to restart. It's not funny anymore. Well, at that point, I got so annoyed that I thought of using those graphs as a visual aid. Not the kind of visual aid you think a visual aid would be. Never mind. Right, so what you basically do is you start reading the code, and whenever you've understood a certain bit of code, you color the graph blue or whatever, you color the graph at that point. So the graph will slowly get colored, and you see I've taken this branch and so on. And what you do after a while is you basically decompile like you peel an orange. The way the graph layouting works, graph layouting algorithms will put the more complex bits in the middle of the graph, while the simpler paths will be arranged on the outside. So something like, if condition is wrong, return 0, will be a path on the very, very outer side. So you start by peeling this graph. You take the outermost branch, decompile that one, remove it, take the outermost branch, and so on. So by this, the graph gets gradually simpler. So complex situations lose the impact they have on you. And it's really, really good to see your progress, because you'll see that you're not as slow in decompilation as you think you are, because you're actually covering quite a bit of code. As an example, we got the RTL free heap function in 2K. And it kind of looks messy at first glance. I mean, I wouldn't know what kind of C code would generate all that crap in the middle there, not right away. So I started the first node. So we got the standard function prologue of, NTDLL functions for most of this block. At the very end, they move some variables around, and then they test whether the third argument to the RTL free heap is 0 or not. The third argument to the RTL free heap is the pointer to the block that's supposed to be freed. And if that is a null pointer, the free call is not supposed to do anything, but just return success. So if it is 0, it'll branch to the outermost layer node on the very right side and move AL1, which means return success more or less, because it'll move 1 into EAX and then return. So we've understood our first bit of code and write it down, and then we remove those 2 nodes which we just covered. The next node takes the pointer to the heap, the heap handle, adds something to it, ORs together a few flags, tests whether they're set, and if not, jumps to the node on the far right. The node on the far right does nothing but call RTL free heap slowly with the same argument as RTL free heap was called, and returns. So you decompile that as well, which is very simple. If flags are together with the flags in the heap, ended with a certain flag mask, have any bit set, return RTL free heap slowly. And then you remove that from the graph as well, and it gets simpler. And you just iterate this over and over again. So graph coloring helps massively to see your progress. It helps massively to keep track of the amount of code you've covered, and it makes sure you don't miss code branches. Because what happened to me frequently is I I was skipping over a branch and telling myself, I'll look at this branch later. And then I forgot about it. And something important was happening in that branch. And I was like, hey, this isn't in my decompiled code. What's the matter? So another nice side effect is you can show results. Because usually if you're spending a lot of time decompiling, the people who are giving you the order to decompile or whatever will not really understand what you're doing. You show them nicely colored graphs, they will be very happy. Another thing is, well, the reduction. The reduction of the graph really helps coping with annoyingly complex situations. Because the structure of a function can look or can be relatively unobvious in the beginning. Well, then the graph reduction helps you in keeping your morale up in terms of, hey, I only got 6 nodes to go. It'll pay off to spend 1 hour more now and finish this. And it'll make sure that you're working fairly complete as well. So as an example, I pretty much decompiled RTL3 heap up until all the nodes which are colored red. At which point I had this situation down there. Whoa, gotta make sure I don't trip. Down here, where I didn't really know what was going on anymore because I had 2 branches and they were merging somewhere down there. So I decided I'll just reduce the graph, and this is what the new out was like, and the new layout was like, whatever. And I could just continue working on this. I got simpler and simpler over time, and it really helped. Another application for graphs is fuzz coverage analysis. First off, I have to warn you up front. Dave, Itel, and me always have well, discussions about whether fuzz testing is worth anything. I know that like most bugs in closed source software are found using fuzz testing these days. I'm really not much of a fan of the approach of throwing, well, trying to brute force an exponential problem, which fuzz testing is in its core. So fuzz testing itself is highly inefficient. The problem is if your fuzz tester does not speak exactly the same protocol as the application you're fuzzing, it'll fail. Or for example, if you have, let's say you have 2 double words, a simple protocol where you just submit 2 double words to a server. So normally you'd have 2 to 64 different variations of arranging all bits in these double words. Now, if you don't know the protocol correctly, or if you don't know that the server will discard your message if the second double word is larger than 5, you'll brute force all the 2 to 64 to the power of 64 variations. While in fact you would only need to do, well, brute force 2 to the power of 37 or something now. So that is one problem. Secondly, you'll never find undocumented features or badly documented features. And one would be surprised how many non-documented features there are. IIS had an almost completely undocumented remote administration language called .htr. Remember the .htr plus bug a few years ago? It was actually fairly funny because what they did is the IIS web server would decide, oh, this request has a .htr at the end. And if it has a .htr at the end, we're going to, well, throw it into the HTR parser. The HTR parser would take the request and scan for the first argument by scanning for a plus in the string, and then execute the file before the plus. So by requesting some file.txt plus .htr, you could execute an arbitrary file in the web directory as a remote administration script. The remote administration scripting language was relatively powerful and not documented. It was a freaking pain to disassemble. Another problem with fuzz testers is it's really hard to compare them. I mean, there's lots of people trying to make money off those things these days. EI, I don't know, I think Hailstorm is another one. So how do you compare products? I mean, they do black magic. They throw large amounts of crap at an application. So a good analogy for fuzz testing pretty much would be you're trying to shooting bats in a dark apartment. And you never know whether you're actually standing in front of a wall or whether you're aiming into the room because it's completely dark. So you might be standing in front of the wall and shooting the wall for hours without hitting anything. And we can use graphs to at least, well, make you know or make you have a map of the dark room, so, or of the dark apartment. So what we're going to do is we're going to do something similar to what Microsoft did. We're going to generate a flow graph. We're going to set breakpoints on every graph node. And then we're going to fuzz the application. And whenever our breakpoints are being hit, we're going to color the node. So we see which pieces of code have been touched and which pieces of code have been fuzzed. Okay, so this will have massive advantages to conventional fuzz. First off, you can measure the amount of code that you've actually covered, so you can compare products. Secondly, you can dynamically adjust your fuzzering mechanisms, your scripts or whatever, to cover more code. So if you see, oh, I've sent 20,000 requests to this application, and I have not even touched one more bit of code, you just have to look where the branches are, and you can determine why certain parts of code are never being touched. So, well, I still don't like fuzz testing, and but it looks nice. Let's say it this way. I'll show. So what we have here is a flow graph of the main user input handler of an SMTP server. And well, the fact that all lines are blue comes from the fact that my small debugger, which attaches to the process and parses the graph and so on, tells me it is there and it is attached to this graph and to the application by coloring the nodes blue. So what we're going to do now is we're going to connect to port 25 and try a few things. And we can see which nodes have been touched. We see that the graph gets bluer and bluer over time. All right, so that's pretty much it. Any questions so far? Okay. All right, let's move on to something more interesting. Pointer and control flow graphs. Well, one of the problems when you're dealing with automated binary analysis is that lots of information from the compilation process is being lost. Specifically, all information about structure data layout. Now, most overruns or most data is not stored in the stack somewhere, but in some kind of dynamically allocated heap structure, and there's buffers in heap structures and pointers in heap structures and so on. So if you look for buffer overruns, you'll have to do or buffer size arithmetics. You need to check whether, well, the source buffer of the string copy is larger than the target buffer and all these kind of things. So without knowing the size of individual structure members, you'll have a relatively hard time of doing anything useful. So normally, one would need to reconstruct these structures manually. And I actually, 2 years ago, I was still doing that more or less. Not 2 years, well, 2.5 years ago. And I spent literally weeks reconstructing structures in applications. I'd identify a pointer to a structure, and then I'd walk forwards through the application, seeing where this pointer goes, and well, adding structure members in IDA, and it took forever. And then once I was done, the next update was out, and the structure changed subtly, and I'd have to do it again. So one can use specialized graphs to solve this problem pretty nicely. First off, we need to identify a pointer to a structure. Identifying a pointer to a structure is really not hard. If you have some pointer where there's a positive offset from it, somebody's either accessing a specific member or a specific index into an array or a structure. But for all practical purposes, an array is a structure as well. It's just a structure with, well, the same structure members over and over. So whenever you see a positive offset from a pointer, you know you most likely have some kind of structure. So the only thing you need to do is, well, identify a pointer and then follow it wherever it goes, which is the more work-intense part. But if you follow it to all the locations in the program where a bit of code has control of this pointer, and then identify all positive offset from this pointer, you have a relatively accurate description or representation of what the structure would have looked like. So building these pointer control flow graphs is not that hard either. More or less, you start tracking code at a certain location, and, for example, start tracking a specific register, EAX or whatever. So you trace the code downwards until you reach either local branch, or read or write access to a variable, or optionally a far branch, meaning a call into a subfunction. You might want to recurse into the subfunctions, but I'll explain that in a few minutes. So if you encounter any of the above situations, you'll need to do different things. In case of a local branch, you don't really care. You do the same thing as you do with the flow graph, because you want your data flow analysis to be, well, flow sensitive. You want to know, well, if there's a branch and a certain bit of code is being skipped and so on. Now, you just do the same as with the normal graphs in that case. Secondly, if you have a write to your register, you abort the tracing, because the pointer you're tracking is no longer there. It has been overwritten. In case you have a read from the variable or register you're tracking, you split the graph, and now you follow both the target of the read and the source of the read. Which means if I trace EAX and I see an instruction like move EBX EAX, I'll have to trace both EBX and EAX afterwards. If I see a move to a structure, I'll have to trace both the new structure variable which it was moved into and EAX afterwards. If I see a move or a push, I'll have to take care of that as well. And in case of a non-local branch, a far branch, more or less, into a subfunction, you might want to decide, or you'll have to decide whether you want to recurse or not. Tracking passing of arguments into subfunctions on x86 can be a bit annoying due to the x86 way of passing arguments, namely on the stack. So you have to track quite a bit there. The code gets really, really annoying. Oh wait, I'm going too far. So going back to the SMTP server which we have, this is the main user handler which we just colored in the graph. And down here, is that readable? Well, down here we see that arg4 is being, well, loaded. Then a positive offset from arg4 is being added to it to calculate an address of a buffer inside the structure. And then strchi is being called on it. So somebody is looking for a new line character in that buffer, which is inside of a structure. So you already think that this will be a structure. And down here we see even more positive accesses from the pointer in arg4. arg4 loaded in EDX, positive offset, some values being moved there. So in the old days, one would start now by going into the structures window of IDA, creating a new structure, start adding a structure member, namely at offset, what was it again? B08 hex, which is 2824. So we first generate an array of 2824 bytes, and the next structure member would be, or the next one would be ours. So we then go back, hit T, make it a structure member, scroll down, see the next one, 4872, so we go to the structures window, do the calculation 4872 minus 2824, and at the next one. And we repeat that forever and ever, and if this pointer gets passed into a subfunction, we need to track that as well. And we'd grow old and wrinkly, and we'd never get anywhere. So, well, I've written a plugin about a long time ago. I can remember working on the plugin on 9/11 because I was sitting on my desk when my flatmate came in. Never mind. So I think it was done sometime around that point. well, it's old, that's what I wanted to say. So you run it in IDA, you hit Alt-1, you get this nice dialog which tells you at which location to start tracking something. You tell it the name of the structure you want to create. You tell it which stack variable or register to trace. In our case, it's arg4. And you tell it push recursion, which means please recurse into subfunctions, but only C declaration. This plugin supports both tracking into subfunctions through registers and on the stack, because in C++ code, for example, the this pointer to an object will be passed in a register most likely, while all arguments to a method will be passed on the stack, and you will want to be able to parse both. So full recursion would mean parse both. In our case, we have a C declaration program, no C++ code, no fast call calling conventions, so no registers being used to pass arguments, which means we can use push recursion. So we hit enter. Wait a second, we'll go for no recursion first, which runs through and generates the first approximation of the structure. Which is already not that bad. As you can see, we just saved ourselves quite a bit of work. And we see typical sizes that would be actually used in a structure: 128 bytes, 2048, 256 bytes, and so on. So we've now more or less reconstructed the structure, and the nice thing is due to the fact IDA works, we get cross-references for structure members as well, which is relatively useful if you're tracking pointers backwards. I'll see whether I can find one of the graphs which it generated on the way. No, that's not it. We'll have to do this again to see whether there's a graph. Oh no. My mistake, sorry. Gotta do it again. I'm a bit confused right now. I'll be better in a minute. Oh, I hope the program will be able to display the graph, because it's gotten relatively large. Okay, let's say it this way, 300K graphs are most likely not easily displayed. The problem is that the main handling function does quite a bit of access, or does quite a bit of passing through this pointer, or give it to structures, and so on and so on. So the graph is massively more complex than a regular flow graph, because it incorporates both the information from the regular flow and additionally the information from which register keeps it at this point in time. And if you have the same variable being passed into 3 registers in the course of time and used throughout most of the function, your graph grows by a factor of 3 as well, because every flow is being duplicated. All right, doesn't really matter. We'll just delete this here, and delete this as well. And then we'll run the plugin again, this time with full recursion down, or with full push recursion, which should give us a better approximation than the one we originally had. And we see that, we'll first collapse everything and then we'll see. We can see that the more code we cover, the more accurate our representation gets, as if you cover pretty much all code in the application which uses this particular pointer or which uses this the structure in general, you can be relatively sure that you haven't missed much, because, I mean, what sense would it make to have structures of which you don't use the members, or which doesn't mean that it doesn't happen, but well, anyhow, this is a massively better representation than the one we had above, and it means that the quality of your reconstruction improves with the amount of code you cover. So let's speak a little bit about class reconstruction. Basically, what is a class? A class is nothing but a data structure associated with a bunch of methods, which are a bunch of functions. So more or less, if you just parse all these functions or parse a bunch of functions, you can reconstruct the class as well, like the class data layout. And all functions have the pointer to the, like all methods have the pointer to the structure in the this pointer, which is on a Visual C ECX usually, and or on a GCC the first argument on the stack. So we'll demonstrate this at with the HTTP request constructor. All right, so this is the constructor to the HTTP request. And what we can see here, first off, the HTTP request is directly derived from HTTP request base, because the constructor just chains through to HTTP request base, and then afterwards adds a few initialization things for its own variables, which the base version or the basic version didn't have. So what you're going to do, or what we're going to do, is run the plugin. For now, with no recursion, and that's just the graph layout program that died in the background. And we're going to track ECX. So we see we've reconstructed this part here. And we can also see, whoops, I'm going to delete this. Okay, we got to run this again, sorry. Call it HTTP request, run it with ECX, hit enter, and look at the structure. And from this point, we can already see what the size of HTTP request base more or less is, because our structure looks like this in the constructor, which indicates that there's the HTTP request base of size 2656, and then a bunch of other things like variables which the original structure of which, or the original class of which this class is derived, does not have. So yeah, that's pretty much one thing. We can look at the graph which was generated, which looks like this. I'll flip back to IEA. Oh, the addresses aren't quite right, so we'll have to look at this one here. Okay, so this is the pointer control flow graph generated for this small constructor. Basically, it tells us that from 65 D5 2A 5B to 65 D5 2A 5E, the register ECX is the only register which holds the pointer to our class. We can verify this. From here to here, ECX is the only register which holds the pointer. Then we have a move ESI ECX, which means ECX is being moved into ESI, which means we now have two registers holding it. So from 65D5 2A60 to 65D5 2A7A, it's in the register ECX from 60 to 7A, where ECX gets overwritten down here. Well, and from 60 to D4, which means 60 up here, D4 is way at the bottom. It is in ESI, where it gets moved into EAX, where the last split at the very bottom in the graph comes from. So just to illustrate on what is the underlying methodology under the object reconstructor. Okay. Now, other interesting things we can do is, well, I'll get to that later. Right now, we're going to reconstruct the entire class, not just the topmost class, but we're going to reconstruct we're going to recurse into all sub-functions, which means we're not only reconstructing HTTP request, but HTTP request base in one big swoop. So we just check full recursion, call it HTTP request, or we call it HTTP rec2. Let it run. It'll take a while because it has a little bit more code to cover, and I'm getting entangled in all these cables here. Jeez. No, I'm not a dance act on stage. All right. And here we go. And we see that the structure is fairly accurately reconstructed. We see it mostly contains pointers. With a few buffers in between. All right, so we just can continue. Or we'll just continue for a bit here. Oh well, okay, so much for single function or constructor class reconstruction. Generally, it's a good idea to start with the constructor because by very definition, a programmer should initialize all class members in the constructor because otherwise things will get very dangerous later on when certain methods are being called without the class members being initialized. Therefore, it is a good idea to start with the constructor because if it has to access all structure or all class members, it therefore will get a relatively good representation. Now, the next thing you can do is, oh, wait. Just an example of how ugly a graph can get. This is a graph of, well, the this pointer all the way through the entire HTTP request constructor. So, yeah, it's ugly. So the next thing you can do is vtable parsing. Vtables are tables in which all virtual methods of a class are being stored, which is good for us because it's basically an array of functions which all operate on the same data structure and which all have the pointer to the structure in the same register. So by parsing the entire vtable, we get a very, very accurate representation. This will work like this. We look for the HTTP request vtable. Here it is. And we check the vtable parsing mode, which means the plugin will call every function in the vtable with the same settings as this, so you don't have to manually go on every function and so on. So just hit enter, let run. Ignore all the warning messages it churns out, and one second. And you get this reconstruction here. Which is most likely about as accurate, if not more, or, well, about as accurate as the constructor. Now, what you can use this for is automatic detection of some bugs already. Because you can automatically detect now whether all structure members have been initialized properly. Basically, you do it by like this. You start reconstructing the structure once using the constructor, and then once using the vtable. And if the structure reconstruction, which you got from the vtable, has structure members defined, which the one from the constructor didn't, you know there's members in this class which have not been properly initialized in the constructor. So just as a neat thing to do. So to sum this part of the talk up, well, we can automatically reconstruct data layouts of structures and classes by doing forwards data flow through the application. We can get graphs which will crash the graph displaying program. Now another interesting thing is RPC interfaces such as COM, DCOM, COM+, pretty much export something called interfaces. Interfaces are nothing but vtables. So we can very, very reliably automatically reconstruct COM objects and DCOM objects, which is very nice. Something which I want to do in the future, which is down there in blue, is Well, after the reconstruction, I'm going to use the type info from the binary to reconstruct the type of the individual structure members. Which means if you have a string copy, for example, being called on a structure member, I know this structure member is a buffer, the char array. Or if I have a pointer in the structure on which is being passed into a string copy, I know this is a char pointer, and so on and so on. So you don't only get the data layout, but you get the data types as well. This will not be done on this code though, because I'll show at the end of the talk. I'm working on something to make the object reconstruction CPU independent, so it'll work not only on x86, but on Spark, PA-RISC, and PowerPC as well. Any questions concerning this so far? None? Can't believe I'm that clear. All right. Last part of the talk, buffer definition graphs. The problem is, well, the problem which prompted me, or which I was prompted with to come up with this was, I need to do buffer size arithmetics, and I had string copy calls and other calls, and I didn't know where the pointers which were being passed into this call came from. So I had to manually trace upwards, which is a bit like the forwards tracing of the pointer for the object reconstruction, where you, there's the first argument to this function is being passed into the string copy. So you look at the 50 different locations where this function is being called and start tracing from every of the 50 locations upwards what the first argument was. And all those 50 locations are being called from another 3 locations, which all take another, well, which all give you a different char pointer. And in order to verify that this string copy truly is not dangerous, I had to verify whether for all possible code paths, there's no way that a smaller buffer is being used as a is being passed into than the target buffer, than the source buffer. Sorry. So basically, you need some kind of inverse data flow to find out where the data which is being passed into problematic functions is coming from. Again, we have specialized graphs which might help. The building of these graphs, of the inverse data flow graphs, is very, very similar to the forwards data flow. You trace upwards until you encounter either an instruction which was target of a branch, or an instruction which writes to your current register, or an instruction which loads from your current register, or until you get a call, and your current register is like EAX, so the return value of the function. So basically, if your current instruction was the target of a branch, you've pretty much found the inverse of the normal branch, which means if you take the normal flow graph which we had before and flip it upside down, all of a sudden all the down arrows become up arrows. Now if you flip all the arrows in direction as well, all the instructions which are targets of a branch are actually the down links in the graph, which means if I'm tracing upwards in the code and there's an instruction which is the target of a branch, I of course have multiple ways of reaching this location, because it's the normal code flow which is sequential and then the target of the branch. So I split the graph in the way I do with the forwards graphing. If my current register is written to from another variable, I just go to the other variable and trace upwards from there. Like if EAX is being tracked and it's being written from EBX, I take EBX and trace upwards. If my current register is loaded with something, I have to analyze the situation and see what's going on there. For example, if I have a load effective address of some buffer, then obviously I found the buffer definition. So I'm done. I color the node blue. Hey, I'm done. And quit tracking. Well, if the current register is the return value of a function, you have two options. Basically, the current register being the return value of a function is the equivalent, or is the inverse of the function being, or an argument being passed into a subfunction. It's just the argument is coming out of a subfunction now, or the value has been coming out of a subfunction. So you can decide to either parse into the function which returns this value, which I'm not doing right now, or alternatively just stop. Problem is that if you have a function like the strchr, if you try to trace upwards through this function, you'll very easily get lost. So it's a more clever idea to just quit at a certain point and color the node red, and well, rely on the user to something. Such a graph would look kind of like this. We're tracking from a certain location, and it finds 4 buffer definitions for a given char pointer. I'll demonstrate that. Okay, what we have here is a call to string copy. We have a buffer as a source of 512 bytes and a pointer for the target. And we do not know where this pointer is coming from. It is the first argument to this function. So normally we need to trace upwards all this code to the beginning of the function, then see where this function is being called from, and iterate for every cross-reference to this function and find out where it's coming from. So instead, I'll run this plugin and tell it to track backwards, namely register EAX at the current location. The plugin generates such a graph here. And tells me the first argument is defined at 40601E, which is here. And we see that the buffer is 1024 bytes large. So 512 as a source, 1024 as a target is not problematic. The second buffer definition is at 4060F9. Again, 1024 bytes, not problematic. The next definition is at 40626F, which is again 1024 bytes, so no problem. Now let's have another example. Again, we have a string copy, this time with a target buffer of 1024 bytes, and a pointer, which is a local variable of which we don't know where it's being set or reset, and so on. So normally we need now to trace upwards in the code and see where this variable was being set last. Here it's loaded, and then some stuff is added to it, and some stuff is being read from it, and so on. This gets quite annoying. No need to do it yourself. You generate a graph, and we see that the data flow for this variable is a bit more complex than the last one. The last one was pretty much just 3 different calls, and this time we got a weird loop in there, which at some point leads to this location, 4D57A, at which we have a buffer of 2048 bytes. So we know now 1024 and 2048, this might be problematic. Yet another example, 1024 byte target buffer, some string we don't know where it's coming from, and another graph. This time the plugin reported that it couldn't finish the tracking, so it colored the last node blue. 40F3FD. strchr. So the application is looking for a new line character or a carriage return character in a buffer of 4096 bytes, and what it returns from there is the stuff being passed into the string copy here. So this pointer here can point to a buffer of a maximum of 4096 bytes length if you have the carriage return at the very beginning. So this might be a problem as well. And one final example. Yet another string copy, 512 bytes target, a string where we don't know where it's coming from. And a relatively complex data flow here. Actually, this function was quite annoying. This function was what prompted me originally to write this plugin, because it's recursive at some point. So you start tracking upwards, and after about half an hour, you notice, hey, I've read this code before. And you're reading the same code over and over again. And well, yeah. So I decide I'm not going to do this manually anymore. 413F74. A 256 byte buffer. Oh no, it's double words. Haha. So it's 1024 bytes buffer. And the target is 512. 434314. Some structure member which is being loaded of size 8,000 bytes. (434661). Another structure member being loaded here of size 8,000, or same structure member at that point. And the last one down here, 411F08. Yet another strchr, this time operating on LP string 2, which we'd have to track backwards further, which I'm not going to do now. I think you've all seen that this massively speeds up the analysis of simple functions. I mean, beforehand, you'd have to track every single pointer backwards, and you'd waste 20 minutes for tracking backwards just to finding out what the buffer sizes are. So this is truly helpful. Any questions concerning this so far, or the inverse variable tracking? Okay. I'm almost at the very end of my speech. I'll pretty much just talk a little bit about what I'm doing right now. As you might have noticed, this talk is almost a year old by now. Or at least I gave this talk last summer already, more or less. The last 6 months were spent on, well, making all this flow analysis CPU independent by writing by designing an abstract assembly language, which is basically a superset of most other assembly languages, very RISC-like, very simple in its instructions to facilitate the analysis code. For example, with x86, you got these insane ways of addressing stuff. You can have something like move EAX, EBP plus EAX, or EBP plus ECX times 8 plus 258, all in one instruction. So analyzing this becomes really, really, really annoying. And at some point, my inverse data flow code became so hard to manage that I decided, no, this is not worth it. Do a clean start. Generate, like, I don't need to cope with the assembly language of x86 directly in the analysis layer. It's much cleaner to get an abstraction layer first. So I thought, hey, you just write a translator from one language to your abstract language, which took a bit longer than expected. But it is pretty much done, and it is fairly stable by now. So I expect to have the inverse data flow and the forwards data flow done for the abstract language, and then I can add more abstract languages. So far, I got only the x86 to the meta-assembly translation, but the meta-assembly is very, very Spark-like. Therefore, Spark will not be much of a problem. I think PowerPC will be relatively okay in PA RISC. So I hope that by the end of the year, I'll have forwards and inverse data flow analysis for 4 different architectures. I'll show the translation process for a second. For example, we take this function here. We generate a regular flow graph of it. All right, and then we run the translation. Doesn't find or doesn't encounter any problems. And now we have the translated code here, which is functionally equivalent to this one here. We see that it stores the frame pointer in a temporary register. Instead of doing push EBP, I kind of rationalized I got rid of the stack, as I think stack makes data flow analysis relatively annoying. So instead of pushing on the stack, they're storing it in temporary registers. The nice thing about a virtual CPU, which never has to be built, is I have unlimited number of registers. So yeah, and it's actually quite nice. Does a lot of interesting things concerning, for example, under NT, or NT bullshit, under x86, you got a rep move SD, which is basically a loop in one instruction. So as my meta language doesn't have that, it de-optimizes this loop. There's a whole bunch of de-optimization things against strange things that compilers do. Specifically, if this compiler omits the frame pointer, this will de-optimize it. And well, I'm quite happy with it so far, because I can translate large amounts of relatively optimized code. Still has a few problems with the fragmented functions which Microsoft is building right now, because it relies at some point on IDA's information. If IDA screws up so badly, my layer doesn't quite work. But I'll be writing a function reassembler, which basically takes the fragmented functions and reassembles them into sequential blocks soon, I guess. Semester break is coming up, so I might have some time. Any questions?
How about using graph-based analysis at the runtime? Do you use that? Is that viable at all?
Good question. I've not tried. What do you mean specifically?
Like, I don't know, integrate a flow graph into sort of a runtime debugger so that you can actually trace through and do graph coloring and actually stepping through assembly.
Well, that would be useful, but it's kind of what I already did with the graph coloring. I mean, it is a runtime debugger. I mean, I can't see which graphs which nodes I've touched without having a debugging interface. But yeah, I mean, graphs are always nice. Data flow graphs, for example, in a debugger would be nice. I have to admit that I'm really not much of a fan of dynamic approaches because I want to do some ROM disassembly. I want to have a static analyzer more or less. So I don't know whether I'm the right person to ask what to do dynamically. Furthermore, dynamically, you don't have the infrastructure which IDA provides you for with like the graphing and so on. So you need to do the combination of IDA and the dynamic debugger and the graphs. Because, well, I don't feel like writing my own disassembly engine to generate the graphs from memory. I'll just use IDAs. And therefore, you need a very, very good disassembly engine in your debugger. And if you want to do data flow analysis, you're pretty much screwed because you need a really, really good disassembly language which has to keep track of stacks, of structures, and so on. Any other questions?
How do you verify the results?
Verify the results, and how far I verify the correctness of the translation, or, well, with the correctness of the translation, I don't. The only way to get the translation from the x86 language to the meta language provably correct would be to have a bijective mapping between the two, which means I'd translate x86 code to the meta language and translate it back to x86 again, and would be identical all the time. And then it would only be like provably correct from the direct translation, and not be provably correct from the semantics perspective. So all my analysis I do on top of that meta language assumes that the translation is perfect. Well, I mean, I gotta assume something. Any other questions? Well then, thanks. And if you want to, or if you have any more questions, just feel free to catch me over coffee somewhere. Or, oh yeah, a few of the plugins are available at Black Hat's website. The object reconstructor, the x86 graph, and I'm making another plugin public, which is the new function grapher. Pretty much, I have two graphing engines. The first one, which I used for the graph coloring, is something I taught myself C++ with 1.5 years ago, and is really, really bad. And I pretty much, for the translation, I had to develop a new graphing engine. I ripped that graphing engine out and added a nice output with syntax highlighting and all the crap. And the syntax highlighting flow grapher, I'll show it again. That should be on the website within a few days or weeks as well. So, all right, thanks a lot, and see you around.